Good morning, everybody. Welcome back. Thanks again for the meeting organisers. Splendid occasion. Great to see everyone again. And I'm going to just move over to Mike Meylan, the first talk of the day on that topic.
Thanks a lot, Dave, and thanks very much to the organisers. It's great to be here, as always. And it's quite amazing that 5 years have passed since we were here for the original meeting. I find that quite incredible. And I'm pleased that the English weather's lived up to its reputation today. I'm a little bit shocked by the heat I've experienced on Saturday. So I've got a couple of confessions to make before I start. One is I haven't had a coffee this morning, so hopefully I'll be able to stay awake. And the second one is that when I was preparing this talk, I had this plan that I'd do it on a topic I hadn't actually done the research on yet that would motivate me to do it. So probably wise for myself to give myself some incentive, but I haven't quite completed the circle on this, but I'll tell you at least about as far as I've got on it. And I wanted to talk about this problem of piezoelectric plates and wave energy conversion because it's a topic that I've been funded to do research on, and it's another it's a problem that should be solved by the Wiener-Hopf and can be solved by it, and it will produce hopefully something that's a useful solution for other people who are working in this field to use. So just really quickly, hydroelasticity is exactly what it says. It's what's on the bottle. It's elasticity and fluids coupled together, and it's a topic that I started working without actually knowing the name because I was originally studying the problem of sea ice, and it has a lot of applications. And because elasticity, things bend, as we know, and bending structures are everywhere, and fluids are everywhere, and then you've got this combination of the two. And the field keeps appearing in different places. It gets new applications seem to appear of this problem, as you can imagine. So the most significant point is that people have decided that maybe flexure, we're looking at problems in wave energy conversion, maybe we can use this flexure, we can use hydroelasticity to produce wave energy conversion. So I'm going to talk a little bit about just the topic of wave energy conversion before we start into the mathematics. So we haven't succeeded in making wave energy converters. We have not succeeded in extracting energy from waves. And it's a bit like de Gaulle's famous quote, to paraphrase de Gaulle, it's wave energy is the energy of the future and always will be. Because it just is a very, very difficult problem to solve, and it's quite interesting why you can't solve it, what all the problems that are involved in it. I could spend a whole talk talking about very negatively about it. But human ingenuity being what it is, surely at some point we're going to work this out and we're going to crack it, and the energy's there, and it's relatively reliable, and it's a relatively high density because fluid motion has a lot of energy in it. Waves have a lot of energy. All right, so there's just a whole lot of problems. One of the things is, it's a bit like back in the day, people were trying to be the first person to climb the north face of the Eiger. And the advice given to the people who were attempting this was to first visit the graves of those who'd done it before. So with this wave energy converters, there's these wave energy parks where people can go and install their prototypes. And what happens is someone comes up with an invention for a wave energy converter and they put it into the laboratory and it works really well. Everything goes fine because at the laboratory scale, everything's much stronger essentially. The same reason why an ant can lift it 50 times its own weight and a poor elephant can barely stand up. So once they go out into the ocean, they're sort of deployed typically, they start to work well, and then about a week later a big storm comes in and they sink to the bottom of the ocean and they join all the other wave energy converters that litter the ocean floor around these wave energy parks. So the first thing, I won't answer the phone from, the first thing you should do if you want to develop a wave energy converter is to visit the graveyard of all the other ones on the sea floor that have failed. I'm quite proud here of this picture here of this wave energy converter because I asked one of these AIs to draw it for me. It did a great job. I'm not quite sure how this is working, but there's your picture of it. Gave me a colourful picture. All right. But what happened, the most successful in a lot of ways wave energy converter, unfortunately it's more than a decade old since it failed, was this Polaris. And it was built by these Scottish engineers. And what they had these modules that flexed. So flexure was actually intrinsic to it. So this isn't the flexure is not the typical approach. The typical approach is just to have something that bobs up and down in the water. And so they built this, and it's called Polaris. And you can sort of get it, there's a picture of it, and they actually deployed it in, they built a farm in Portugal off the coast. And it ran for several years, but the problem was the cost of repairing it was so great. It was the survivability that was the problem. It just, basically all the money was, any money you got from the electricity it made was lost in repairing it. And then it was abandoned. It's rather unfortunate because you kind of have a feeling that had they stuck at it and learnt from their mistakes and worked out and made a better and better version, worked out what failed, they actually might have succeeded with it. But unfortunately that never happened. And then as this whole line of got abandoned. And I guess, if you're an investor investing in wave power, this one's failed, you're probably not going to want to put money into a similar system. So, but it used flexure. There were rigid parts with a flexure, so you could almost, that's almost a similar model to what I'm going to show here for this piezoelectric wave energy converters. So this is just a few slides I've taken from various, a bit of Google searching for funded projects on flexure. So this one here is something from Wave Energy Scotland, where they're going to use flexure. There's this one here, some funding for the University of Plymouth on wave energy by flexible material. And there's lots of ways you could use flexure to get wave energy out. Like you could have some tube that bends, some rubber tube, and that forces a fluid, and then you drive that to get energy out of, or something similar. And it's interesting to talk to these guys because they've done a lot of experiments that they've conducted in the laboratory on these various systems, and they haven't really been able to analyze them mathematically very well. So there's quite a disconnect between the mathematical analysis of these systems and the experiments. And it's part of the problem is that you can't just console this because the mathematical tools haven't been developed that can take into account the flexure or to model these complex flexible structures. And it's not entirely clear what mathematics you'd use to say model a membrane or some kind of structure that they're experimenting with. And here's another project here. You can see the ideas people have got. So, and I think a lot of this is just the realm of the mad inventor in a way. But this is some giant rubber thing that's going to flex and produce energy. And that would be through some sort of piezoelectric action most probably. And then the upper one is some sort of tube. And maybe you could drive some kind of turbines from the fluid in that tube. But and you can think about why this kind of rubber flexible object might be a really good idea, because it's not going to be as, it might be more survivable and more capable of doing large deformations and of absorbing forces and things like that. So now I'm going to talk a little bit about the Wiener-Hopf method and the history of this floating elastic plate, because this is the problem we're going to look at and solve for our piezoelectric wave energy converter. So it's quite interesting, the history of this problem, and you get more interested in history as you get older, but the first solution to this problem was done during the Second World War, when they were, and I think in connection to the design of the Mulberry Harbours and things like that. And it appeared in this book by Stoker, who wrote a famous textbook on water waves, and he described the solution. So the problem goes back, it's the first sort of problem in hydroelasticity. And in fact, the reason it appeared in Stoker's book is because Stoker was on the original report. And you can actually find that report now. It's been digitized, but of course it wasn't known in any way until very recently. And then David Evans, who some of you here will know, was a professor, and he actually worked a lot on wave power. He tried to solve this problem by the Wiener-Hopf, and he never published it. And it got published in this obscure report. And he went up, many years later, I asked him, what happened to this work? Why did you not publish it? And he said, well, I submitted it to JFM, got rejected, and then he sort of gave up and moved on. But there's a strange kind of story happened where Vernon Squire, who was my PhD supervisor, saw a copy of this report. And then from there, the ideas in it kind of started to permeate out. And the first solution, but very closely based on it, was actually by just eigenfunction matching, which is this kind of brute force approach to solving the problem. And then in 1995, there was a review paper on these waves in ice, and it brought this topic into greater interest. It exposed it, and a lot of applied mathematicians and various people became interested in understanding the system of equations. And then, as often happens, the actual Wiener-Hopf solution for this problem appeared in the early 2000s, and 3 different people independently, I'm certain that they were all independent, produced the solution around the same time. So there might be a year or 2 different in the publication, but there was a group in New Zealand who I know well and have worked with and collaborated with who did it, and Barnforth and Richard Craster in the UK did it, and Chikeva did it, produced a solution in Russia. She's from the group in Novosibirsk. And it's quite interesting, they all had very different approaches, as is often the way, and the Chikeva paper is very interesting because she did the solution in infinite depth and did it on Riemann sheets. And she actually ended up producing a very simple formula, which has proved really useful. But that work by Chikeva has not really been, I think, understood, or there was no lineage from it, and partly because of the isolation of the people working there. I don't think Chikeva's ever left. To the best of my knowledge, I've never met her at a conference or anything like that. All right, so now we'll talk about piezoelectric wave energy conversion. So is this going to work? I don't know. And if you talk to engineers, they're like, this has just got so many problems, and it's not necessarily something it's not something that I'd start putting my money into. Let's put it that way. I'm putting my scientific research into it, but there's a lot of challenges involved in it. But it seems like, in theory, it seems like an idea that makes sense. We know that piezoelectric materials, when you bend them, they produce a voltage. So if you put something into the fluid that's going to follow the wave, curve with the wave, flex with it, and then we can simply harness that voltage and produce power. And of course, and it would probably work really well in the laboratory. Would it work well in some huge storm sea? We don't know. And it began with this paper of Renzi in 2016. So he actually postulated and developed a solution. It's the only paper that he wrote on this topic. So I don't know if any of you know him, but he seems to, I don't know what motivated him to solve this problem. He just came and decided to work in this area. And it adds an imaginary part to the flexure effectively. So we'll talk a little bit about that. One of the things that's important to note, though, I think in this all of the work that follows, is that if you have a material, if I move it, and I'll give it a first derivative, I don't put any energy into it. But if I put a second derivative, if I bend it, I put energy into the material. And if you design some kind of wave energy conversion using flexure and you're removing energy proportional to the second derivative, all of this analysis will apply. So it could be some other mechanism than piezoelectric. For example, it could be some way that you're forcing the fluid to move as it bends or something like that. So it's anything that absorbs energy in the second derivative. So from bending, this will apply. So this is the schematic diagram taken from Renzi's paper. So he actually went as far as trying to work out the equations for a piezoelectric material. So he had piezoelectric patches glued to a substrate, and then he derived the equations. It becomes quite complicated because you have to then have a circuit equation to close the equation that's removing power, and you get the flexure of this object is combined by the flexure of the piezoelectric and of the substrate, and he went as far as putting in realistic parameters for the piezoelectric material, which is something I haven't actually done. I've just done it in non-dimensional sort of theoretical units, or made-up units if you want. But this derivation is really interesting in itself, and if you talk to people who are experts on piezoelectricity, or the piezoelectric effect, there's a lot of subtleties to it because the material is highly anisotropic, and it has different properties, flexing in different directions, and all of the stuff. There's a lot more to trying to put this together than just, it's not clear that the analysis that was done in 2D would apply to a 3D and things like that. Like, there's a lot of work just on the piezoelectric theory that needs to be done to make this, to kind of close it. But as always, we assume the problem's linear, and we assume that we have a single frequency omega. So that's going to greatly simplify the equations, and it's going to greatly simplify the analysis of the system. And I just introduced these variables here, phi for the velocity potential of the fluid, and eta for the motion of the fluid surface. So that and we're imagining the plates floating on the surface of the water, so eta will be the motion of the plate, or it could be the displacement of the free surface. So this is the equation from what Renzi derived for the equation, and what he found was that the D is the flexure if you had no piezoelectric effect, and then he added in this frequency-dependent imaginary part, because it's imaginary because there's some force that's acting at right angles to the motion, due to the electric effect. That's going to remove energy, and the effect of this term is highly frequency dependent. So for low frequencies and high frequencies have different properties. And then in my analysis, I'm just going to consider, since we're fixed at one frequency, I'm just going to define a real and imaginary part to this term here. So I'm going to just simplify it down to this real and imaginary part. But this imaginary part should be frequency dependent and should depend on the exact geometry, all the piezoelectric effect, all of that stuff. But for us, once we go to this problem now mathematically, we're going to solve it for any imaginary beta I and any real beta. So we're going to construct a solution, but the actual simulations that I'm going to do are not going to be done in this for an actual piezoelectric material which is frequency dependent. I'm just going to assume in my results that the beta is a constant, just to keep it simple. Okay, so it's not really very different. We've just added an imaginary part to beta. So all of the machinery that could apply before is going to apply, and that's essentially what I'm going to do. So it's not greatly extending any of the theory that's been developed. So this is a schematic diagram of the problem, and we're going to get into the equations here and derive the Wiener-Hopf solution from this problem. So I've tried to write this perhaps not totally clearly, but this is the fluid surface, this is the plate. This equation here applies under the plate, and this equation here applies at the free surface, and this equation here applies universally. So there's certain features of this problem that you need to be able to get the Wiener-Hopf solution to work. Like, you've got these global relations. So this solution here applies globally, and so does this one here. So you're only really left with the one equation that's on the surface that changes. So effectively you can reduce the whole problem down to being one-dimensional. And if it didn't have that property, then it wouldn't, at least with my knowledge, it would be very much harder to solve this problem. And of course, if you added more plates in or you started to change it, you could end up getting into something like a matrix Wiener-Hopf problem. And they can really easily arise from generalizations of this. And in fact, one of the things that we really would like to do is to look at trying to solve for more plates, because it would make sense if you're going to build this system to have more than one plate, to have multiple plates here, trying to absorb the energy. And in fact, the plates that are in the fluid will probably be more effective at absorbing it. All right. So these are just the equations of motion, more or less just repeating what was written there. So we've got Laplace's equation and this impermeable bed condition. So the water waves have this advantage that they are governed by Laplace's equation. I don't know if it's an advantage or a disadvantage. And you so you don't have those waves are boundary waves. And you can generalize this to Helmholtz equation. It allows you to have waves coming incident at an angle, and it will be easy to generalize this equation to that problem. And you could also probably extend the analysis to having the actual velocity of sound in a fluid. And that's something that is not going to arise in this problem, because you only start to see effects of that when you're looking at things like tsunami waves. But the analysis would probably carry on. The Wiener-Hopf method could still solve that. You're going to have a tsunami wave impacting on the plate. But let's hope that doesn't happen. So this is the equation that jumps. So you've got this boundary condition coupling the velocity potential at the surface, and it changes at the at x equals for x greater than 0 and for x less than 0. So that's, you've got this in two parts. So, and naturally it's going to turn into a Wiener-Hopf problem. And we have the only thing that's left in this problem is the edge conditions of the plate. So one of the challenges is how to incorporate and solve these edge conditions. So we have the second and third derivative vanishing. And that condition, when we build our Wiener-Hopf solution, we have to impose that condition at the end. There doesn't seem to be a way to build that into the actual solution. I'm not sure that's it. So when in the end you end up with the formulation with these two unknown coefficients, which naturally arise, and then you have to solve for those at the very last stage of the solution. So,
Mike, did you take plus I omega t to have the beta with a negative imaginary part? I can't remember.
I thought I did minus. I've done this in a little bit of a rush, and I'd have to say that any minus could be a plus.
Yeah, so you had eta was minus I omega 5 before if you had e to the minus I omega t. So I just wondered if you changed it to a plus. But we won't mind pluses and minuses in this.
I can't remember if the computer code by rote works with minuses or pluses here. Yeah, that's right. Yeah, I have to say that that's, and when I say in the upper half plane, I might mean the lower half plane, but yeah, sorry about that. I think that the Renzi, the derivation, that's what Renzi had. I think it should, we'll discuss it later. Don't get an argument about it. Yeah, don't ask any technical questions. Yeah, so we've got to get rid of the incident wave. So we assume the incident wave is of this form e to the ik naught x. That's the incident velocity potential, and then we subtract those to get the scattered wave. This actually wasn't what was done by, I'm largely following what Chung and Fox did, but they didn't actually do this step here. They did a slightly strange thing where they removed the transmitted wave, but this makes a lot more sense to me. So you end up getting now you've got a system of equations and the scattered potential. The only problem being that the scattered potential doesn't have such simple boundary conditions at the edge. All right, so now we've got, and so the introduction of the scattered wave potential, because the incident wave satisfies the same boundary conditions, it doesn't appear for x less than 0, but it appears in the right-hand side, and this is the driving term of the system. This term here that exists for x greater than 0. And then we have this relationship between the velocity potential and the displacement at the surface. So we can just basically substitute for eta, for phi, sorry, and get an equation solely in eta. I'm solving in terms of the displacement of the surface. So since that's the thing that I want to plot and drew equations on, whereas in some sense phi is the more physical variable. But you can convert from one to the other straightforwardly. And then we just take the Fourier series as always. So I don't think I need to talk too much about that. I'm using the notation alpha for just following on from what is standard in this area, rather than, I guess this is not standard in other parts of mathematics. It's probably not what you're going to see in the Wikipedia definition of it. Okay, and then as always, the contour is, deformed around the poles that are on the real axis. Okay, and then I define the plus and the minus exactly in the standard way here. Hopefully I've got that plus and minus the right way around here. Okay, good one. All right. So then, when we take the Fourier transform, we end up with the system of equations here, and we end up with this very annoying term that arises from the fourth derivative, this m3 of alpha, which is not an unknown. It's not this. It is actually physically part of the problem. It comes from these boundary conditions, and some of these we'd actually know, like the second and third derivatives of the function a to s we know from, so we could actually substitute for those. Now, one of the solution method, which is directly taken from ideas in this Chung and Fox paper, they actually eliminate, and we're going to eliminate this M3. It's quite ingenious what's done to get rid of it. I think that's because it can arise as a very annoying term in the problem that you have to then solve for as well. So you've got this unknown polynomial that appears in the equation just from doing integration by parts of that fourth derivative. But now we're sort of getting down to something that's going to be very like a Wiener-Hopf equation. We just need to do a little bit of manipulation with it. So there's a lot of details here in these slides. I'm not sure how much I need to speak about. And, so we then eliminate the phi and we get this equation here for eta. Okay, with eta plus, one equation for eta plus and one equation for eta s. And then we add these equations together to give us an equation that we can then try and apply the Wiener-Hopf method to. And we attain this equation here. So we introduce these dispersion relations that are naturally going to apply because we know the solutions consist of modes on each side, which are solutions and zeros of the dispersion relation. So there they appear here. And there's the open water dispersion relation and the plate dispersion relation. And though these dispersion relations have been really well, so the numerical solution of these dispersion relations, as always, is the main challenge, but these are really well studied equations. And they are, the open water one is classical, and of course I've got computer code to solve this. And the plate equation has also been very well studied, and I also have code to solve that. The only problem is that this beta now can be imaginary, which is going to disturb the property of the solutions. And that, and so constructing numerically robust solutions to that equation is a little bit of a challenge. And I've noticed that, we'll talk a little bit about the method I've worked, but you can always get into nasty problems with it, which we'll come to. So it's not constructing a very robust solution to these equations is a bit of a challenge. So I talked about here about this problem of solving them. So what I use is a homotopy method, which is essentially you solve it for the real case, and then you solve it. You slowly change the imaginary part and you follow the roots. And that method works really well as long as the roots, because Newton's method is fantastic as long as you know the answer. Right? But the problem, if any two roots meet, it's going to be a disaster. And we know that under some parameter values, the roots will collide. And of course, once you do that, you can't track or follow them. So it's just, the method will definitely fail if two roots meet. And you'll end up only finding one. So as long as that doesn't happen, and if the imaginary part stays small, and you can add other terms into this equation as well, which will make it much more challenging, like the compressive effect or something like, or a tension effect in the plate. This is supposed to be a movie here, which shows you. I drew this morning. Whoops, page up. Here we go. I don't know if this. I did this morning. I thought I'd try and visualize it. So this is a picture of the dispersion relation, and I'm making the parameter more complex. I started out with the parameter being real and only real, and then I added a complex part to it, and you can see that the roots just move a little bit. So the homotopy method is going to work perfectly. I don't know how. It's a colourful picture, but this is showing you this is this visualization of in the complex plane. It's a picture of that function. And for complex, this is the complex plane, real and imaginary part, and then the color, the height of the function is the hue, and the color is the phase. But the zeros appear here as these dots. But you can see they hardly shift, and the dispersion relation has this very nice property that the solutions are all multiples of pi up this axis, so they'll be slightly perturbed, but asymptotically they become like Fourier series. So I think that makes the calculation very stable, and it's not a problem to find thousands of these roots because eventually they're just multiples of pi. So that gives you it makes the numerical calculations a lot more straightforward than say it would be if you had to solve for them. Because sometimes you need a lot of roots of these equations to get their calculations to be stable. For example, these products factorization here, you need a lot of solutions to get it to work. But it naturally these naturally decompose, and this works into this product factorization with the roots. And of course, this allows us to factorize into the k plus and the k minus, as we'll see. There's nothing. This is all. The theory just carries right on. It doesn't matter. And the roots still appear in plus and minus pairs. So if k is a root, minus k has to be a root. It has to have that, and that's just a symmetry because the solution's the same going for waves going one way and going the other in the plate. If you added some anisotropy, that would greatly perturb that. You know, if you imagine some piezoelectric material that was going to absorb energy more in one direction than the other. So there's our system of equations still containing this M3 term. And then this is the trick that Colin Fox and Hyuk-Chung worked out, is that you can observe that the difference between the dispersion equations is this term, and you can substitute that in, and then you get down to this finally you end up with the Wiener-Hopf equation, which still contains the M3. So this is some details of this. Maybe we just get down here to the splitting, and there's the Wiener-Hopf equation right at the end here. I'm going to go through as conscious of the time here. So we end up with this final Wiener-Hopf equation, which still contains the M3, and then this equation here equates to a polynomial, and we don't know the order of that, we have to calculate that, but it turns out that that's of degree 1. It makes sense. It has 2 coefficients in it, which will give us the 2 boundary conditions. So we're still sort of left with this M3 term, but what we can do here is we can add these equations together after manipulating it, and we can eliminate the M3. Okay, here are these 2 equations written down. We get this equation here. Once we've calculated the J1's unknown, and we add these together, and we end up with this expression here, which eliminates the M3. So we get this final expression here for eta hat, from which we can work out the eta, and it only contains the J1 term. So this is the equation, and we've got the solution here. Here are the 2 parts of it. We can use one to calculate the solution in the upper half plane, one in the lower half plane, etc. We've got the formula, and we've solved the problem, the Wiener-Hopf. Now, there is a shallow water limit to this equation, which greatly simplifies the equations, and it's actually only in the system that I've solved the equation. So when I wanted to implement this numerically, I've learned enough, and I've got old enough to realize that this is going to be a nightmare to program, so I decided to program it from the shallow water solution first, and then to go to the full solution with actual fluid depth. And of course the shallow water solution is the one that Stoker solved, and Stoker famously says in the book that you end up with an 8x8 system of equations. In our case it's actually only a 4x4, and he goes, well, that will be very hard to solve. But of course it's not, and so I've got an analytic solution. I've got another solution that I can compare with, so I can debug the code really easy because I know the answer, and I can compare at every point my solution that I'm calculating from the Wiener-Hopf with the shallow water. So I've got as far as, thanks to some work done very recently, I've got as far as the shallow water solution of this equation. But and so this would be a really crazy way to do this. Wiener-Hopf and shallow water would be completely mad, because you can solve it by solving a 4x4 system of equations that, using a sledgehammer to crack a nut. But it's very useful for debugging. And it's also quite cool that I just want to show this really quickly, how you can use this visualization software, because I was able to calculate all these terms and check that they were in fact equal, and equal to this polynomial of degree 1. So, but because I already knew the solution eta plus, eta minus, and I knew these M3s, because I calculated them from the known solution, and then I drew a picture like that. So I found this useful. I don't know if it's very helpful, but I actually plotted the solutions, and I can look at that and go, oh well, it's a polynomial of degree 1, right? It's only got 1 0. So yes, it's all working out. All right. So the last thing I want to do is these time domain simulations. So this is something, when we've solved this problem, we've calculated the reflection and transmission of energy, which is generally what people plot, but I prefer to do a visualization of it, and it's really easy to do. I've tried to explain this lots of times to people, and it's I'm not sure I've ever succeeded. I just wanted to try and make it clear how simple it is. So we have this equation here that we basically simulate in the time domain by just superposition, and we want to calculate that integral. That's the time dependent. That's the formula for the time dependent solution for a lot of frequencies added together, and we can use quadrature, like midpoint rule or something, and we can produce an approximation as the sum. And it's actually, the quadrature, the simpler the quadrature, the better in many ways, just like the FFT uses a really simple quadrature to do the Fourier transform. And then it turns out that if you look at that equation there, it's actually matrix multiplication, where you take the solution you've found in the frequency domain and you multiply it by a vector f. So it's really quick to implement on the computer. So it's very, very simple to do. It's just matrix multiplication. So I'll just try and show some simulations here. So you can see this is just for some parameter values, which I'm not going to tell you. I forgot to put them on the thing, but you can see here the wave pulse hits the plate. The top, we have this imaginary part absorbing energy, and the bottom we have we just have the plate without. And you can see, it's quite interesting to see what happens. So the pulse just moves into the plate. There's no absorption. The pulse just travels along. It has a different wavelength. And most of the energy is actually going into the plate. And then in the top, you can see the energy just propagates and slows down, stops. And it's interesting that the reflected energy at this point is the same for both systems. It doesn't seem to strongly depend on the absorption. And this is the velocity potential. So that has to be continuous at the origin. I don't know whether this is, but just another picture of the solution. So this is showing you the velocity potential at the surface. So the pulse comes in, some part of it's reflected, some parts propagates on, and you can see here that the energy is being absorbed as it propagates along through that plate at the top. And then this is just for a slightly different case here where I've made the pulse, lower the central frequency. The pulse has a bigger wavelength, lower frequency. I think this is quite a good way to. It's sort of, there's not a lot of complication to the reflection coefficient. Of course, you get to work out the extraction of energy, but it shows the process of it. It allows you to visualize and see it. You can see here that the pulse, the energy is getting absorbed more slowly here because it's the bending is less. Okay, and then of course I haven't taken into account. I've just kept the actual imaginary part of this material the same. I haven't changed it as you would have to if it was a proper piezoelectric material, because it would favour certain frequencies over others. And then here's the solution with for some very high frequency packet. But these calculations, once you've solved the problem and calculated it, each one of these equations is just a matrix multiplication, and it takes a bit of time to create the visualization, but every solution's plotted in an instant, and it doesn't have to be, it's not a time stepping solution, it can just plot the solution at any time. So all right, so really quickly, there's lots and lots of problems that could be solved by this. The extension to infinite depth. So in that case there, all those poles line up and make a branch cut, and then you end up on a Riemann sheet. But it seems like it's possible in that, I really have not understood how that works. But if you could, that seems to result in simple formulas, which are really, really useful. And they've proven to be really useful even in this wave-ice interaction. I mean, everybody loves a simple formula for the reflection coefficient. And then there's the residue calculus, which is closely related to the Wiener-Hopf. I've never quite understood the connection exactly, but they're very closely related problems. And then the main challenge is to try to extend this to multiple plates. That's the real challenge, to try to have a system that would allow for more than one floating plate, so a plate submerged in the water. All right, there's my summary, but I'll finish there. Thank you very much.
Very nice, thank you, Mike. Plenty of time for questions, which is great. Everyone's itching to do it. Should we start at the back and move to the front? Yeah. Sorry, Raphael.
Quick one. So when you do your frequency domain calculation, so you fix your beta to be constant, which is fine, and so is the frequency. But when you go into time domain, I mean, that parameter that's supposed to be frequency dependent, do you keep it constant? Or?
No, I have kept it constant, Raphael. Yeah, that's a confession, but it wouldn't be very difficult to change it. The main problem for me is that I feel like I don't know enough about how to calculate what that actually would be for an actual, because then you get down to the kind of physics of the piezoelectric material, which is, I could take the results from that paper by Renzi, say, but yeah, how?
But
You're right. It would be.
Problems.
It does need to be done, and and that would show up in that problem really strongly in that simulation, because the beta would be different for those different wave packets.
Thanks, Malta.
Just a quick comment. When you have the reflection, it's basically the same, no matter if you've got the Piezo effect in there or not, right? But that's probably not surprising because it's reflected off the edge, right?
Yeah, correct. Yeah,
So,
that's
so
right.
Basically, from the edge, basically looks the same to the wave.
And so, in some senses, Malta, you could probably just solve this. Ignore the you could ignore the effect of the piezoelectric material, and just solve it so it wasn't there, and then
Probably.
and then just add the imaginary part in the as it propagates. The imaginary part of the wave number starts to become important, but you could just factor that in. Yeah.
Yeah, but to really get the reflection coefficient and the transmission coefficient, so work out how much energy you have to solve this proper problem.
Yes, and you need to there's lots of next steps which are missing in this analysis. So I haven't time to do it, but you want to look at how much energy is absorbed and try and look at for that for a range of parameters. What's the optimal?
Sorry,
Can I
John.
ask about the second point on your last slide, but one, just before your second topic there. Now that relates to the paper of Tukachiva that
Yeah,
you
that's
mentioned.
right,
Now
yeah.
I have read that,
Oh, you have
and
read it.
it's a masterpiece.
Ah,
It's
excellent.
very, very simple, as you say, and the end result is purely algebraic. It's for infinite depth, but of course the material parameters are real. So my question is, if you simply repeated that analysis,
I think it would work perfectly.
it
Yes.
also
It would
probably the end result
be the same.
would be the same, but make the bending stiffness complex. But surely physically that would be of immense value, because it would give you a kind of parametric representation in this idealized case of how much energy is absorbed. So it
I'm
might give you a
pleased that
kind
you've-
of
I'm
tuning
pl-
analysis
I'm
of where
pleased
you
you-
have impedance matching
Yeah.
to get maximum energy into the plate. So it seems that that would be a very natural thing to do. Perhaps in just an afternoon for someone like yourself.
Well, I'm very pleased that I've met someone who's read the paper, because I'm not convinced that I'm pretty sure I could search all of London and not find another Sol, but and maybe all of Nova Sibirsk as well. But I think I read it recently, and I looked and I agree with it. It seems ingenious what she's done. Yes.
And in fact, I did at one stage read the earlier work of David Evans. It was a Stevens report,
Yeah.
of Oaken or whatever.
Yeah.
And I was astounded. He only did the duct problem, which is hard, and he didn't do the problem for the infinite depth, which is incomparably easier. I mean, I say Tukachiva's work is outstanding, but it's not a very hard problem once you have it for infinite depth.
Okay,
It just
interesting. I'd
falls
like
out.
to chat about that,
Yeah.
because
It
as
is
soon as I
easy.
saw the words
It's
ream and
definitely
sheet,
an
I
easy
started to
problem.
get panic, and like eyes glazed over, and I started sweating, so I gave up.
Can I ask a question about your factorization that you used? So did you use the infinite product decomposition numerically, or did you use some other?
That's right. Yeah,
But you know your formulation there.
it's a bit dangerous.
It's
with
very
that.
slowly convergent.
Yes, it's
Mostly
really
you put an exponential factor
Yes,
into
agreed
the
on that.
two terms.
Well, first of all, I've only solved it for the gone all the way through it for the shallow water case. So in case there's only 3 roots, so it's easy. But the MATLAB seemed to go product, and I tested it. You can calculate this, but you need thousands of terms.
Yeah.
So it's kind of if the computer, but that the question is.
I've sort of given up on that and used Cauchy's integral representation.
Yes,
It's
no, I
much-
agree, and you could
much
apply
quicker
that.
and easier. Any other questions? So I can ask another one. I've got a couple of minutes. Really, so the really important thing is to get the piezoelectric modelling right and work out, as Raphael says, what's the frequency dependence of the imaginary part, how much energy you extract, etc. So how difficult is that modelling then?
Well, the project I'm on was we got funding for this is working with the other people are experts on that, and so we've gone through what Renzi did, and they've agreed that it was right, which I felt good about. But yes, the problem is you've got to have a kind of substrate of some material. You've got to understand how it's poled. There's all these subtle points. It's not like and then you've got to add a circuit onto that to extract energy.
Yeah.
So I sort of looked through that and saw it's just an imaginary part. But you're right. That's the biggest problem, is to make it realistic.
Yeah.
So because otherwise you've just got, I mean,
But it's worth doing because, as you say, Pelham is broke because of the engineering technicalities of it, not the principle of it. And so if you could find a much easier way of extraction, energy extraction, which didn't have all those mechanical problems,
yeah.
and it's much...
And there's a lot of niche applications, I should finish here, for wave power you don't think about. But for example, offshore aquaculture, they got to go out there and replace the batteries. They've got electric systems, and that's very costly to them. So if you could generate energy for them, they don't care if it's, you're not competing with the huge coal-fired power plant, you're competing with someone who has to drive out with a battery. So this would be very effective for that. And you know, in the engineering chapter, there's a different problem to solve. You just need a reliable, it's not a cost thing as much.
We can thank Mike again. Thank you very much.